Hi everyone, I'm Theo and I present joint work with Christina, Markus and Katharina about potential threats in circuit establishment in Tor with focus on the feasibility of traffic analysis attacks. Tor is an application layer anonymity network that can protect a user's identity on the internet. When using Tor, traffic between client and server is routed through circuits, that is, 3 relays called guard, middle and exit relay with individual layers of encryption, so-called onion encryption. Because the encrypted traffic streams look different on each hop, and the connection to the server comes from the IP address of the exit relay, an adversary cannot link the traffic on the server side to the identity of the client. That applies to both protection from external observers, but also from the relays in Tor that are involved in the communication, for example, when they are compromised. Unfortunately, there are several attacks against client anonymity, so-called traffic analysis attacks, uncovering the identities of communication partners without seeing their IP addresses. By evaluating characteristics of their communication, of different patterns in their traffic, packet sizes, timings, and so on. One well-known type of such attacks is end-to-end confirmation, or flow correlation, where an adversary tries to identify pairs of related transmissions at both ends of such a connection. To this end, the adversary captures network traffic, for example by running a compromised relay, or by capturing traffic between client and guard on the one side and exit and server on the other side. Recent work has shown that technically such attacks work with high accuracy and are able to find all pairs of related streams, for example using deep learning techniques like one of the most recent ones presented at CCS 2018. So from a technical standpoint, traffic analysis already works quite well when traffic can be observed. The challenging part is that in order to apply such advanced techniques, there needs to be data that can be analyzed. To conduct such end-to-end correlation, the adversary needs to capture and evaluate large amounts of Tor traffic. And for full correlation of all traffic streams, all traffic needs to be analyzed, which is an enormous evaluation effort. Tor relays currently provide in total 600 gigabits per second of bandwidth, and all traffic currently consumes 300 gigabits. Maybe even more critical is that there needs to be access to all the traffic of interest, to traffic entering and leaving Tor through almost 7,000 relays in different geographical locations. For example, those relays all across Europe are illustrated here. Our paper focuses on these requirements. We explored if an adversary can make assumptions about the routes taken by traffic through the Tor network, in order to reduce this overhead for monitoring and, in turn, improve the effectiveness of traffic analysis and correlation attacks. We assume an adversary who can observe a traffic stream entering Tor by running a compromised guard relay, for example, and wants to know which exit relay is used for a particular circuit to estimate the success chances for end-to-end confirmation. So the question is it possible for an adversary who is able to access traffic of a particular set of relays, either by operating them or having access or controlling some central nodes that must be part of the related connections, and who monitors the entry traffic of a particular client so that we have a targeted setting? Can this adversary determine whether or not they can also access the corresponding exit traffic of this client? Can they determine in advance if end-to-end confirmation will be successful? On the opposite, when it's clear or likely that the counterpart leaving Tor, so the corresponding exit traffic cannot be accessed by the adversary, there is no need to monitor the traffic and to make an attempt to correlate the streams, which reduces the effort by removing attempts that are not promising. So the basic idea we pursue is to predict or guess the exit relay used by a particular client. Our goal is to have a ranking of relays to determine which are more likely to be used in the exit position. Based on such a ranking, an adversary can reason if traffic analysis might be successful or not. And we use some fundamental characteristics of Tor's circuit establishment procedures for this. The first one is rather naive and straightforward. Relay selection in Tor is mainly based on the bandwidth relays provide. The more bandwidth a relay offers, the more frequently it is included in a circuit. It's simple as that. There are also some restrictions. For example, no 2 relays from the same subnet or relay family can be used in the same circuit. So in this scenario, we consider all exit relays, remove those to which the restrictions apply, and for the others we assign a probability simply determined by the bandwidth fraction. This directly results in a simple ranking of exits, ordered by the probability. This is essentially the concept for an adversary to predict the exit. Simply using the bandwidth is quite straightforward, as I already said. The problem is there is no information gain to determine the exit of a particular circuit. The result of this prediction will be roughly the same for each circuit, as long as there is no significant change in the overall infrastructure in Tor. So we built on this idea and adapted it with characteristics of individual circuits. A promising candidate for this is timing information from the so-called end-to-end handshake that takes place when a new circuit is set up. So once relays for a new circuit are chosen, there are individual handshakes between the client and each relay to establish these multiple layers of onion encryption. Since the handshake traffic can be distinguished from other packets, an adversary controlling a malicious guard can measure the timings for handshakes between client and middle and client and exit, and calculate the difference to get an approximate round-trip time between middle and exit relays. Based on this idea, we conducted our experiment, setting up multiple clients to create more than 250,000 circuits, and measured the end-to-end timings for handshakes, and determined individual timings between the hops. Since we knew which relays were used in all of our circuits, we created models for transmission timings for groups of relays. We built groups based on the country a relay is located in, and aggregated distributions of transmission timings for each of these groups. For a newly observed handshake time, we then looked at these timing distributions and analyzed which they most likely come from, effectively resulting in a probability for each exit candidate, therefore in another ranking of exits. We then evaluated the prediction accuracy. Since we know the true exit for each circuit, we simply look at its rank in the prediction and consider the median rank of all prediction for all exits where the adversary has access to traffic, that is, all exits in the same country. For example, when the exit is located in Germany and we use the first bandwidth-based prediction, the true exit is ranked at the 11% relative position in the ranking. For the prediction using handshake timings, the median exit rank is in a similar position, maybe even slightly better. Lower numbers mean better performance since the true exit is ranked closer to the top of the prediction. We can also evaluate this for relays in other countries. For all top countries, except for the US, we see slight improvements for the timings compared to the bandwidth-based prediction. Since both rankings provide us two individual and independent probabilities for each relay, we can also put those two together and generate another ranking based on the combined probability. This further improves the prediction for groups of relays in all countries. For reference, we also tested a randomized ranking with the outcome being as expected. Of course, there's a lot more variation in our paper. For example, we also take into account the monitoring effort for the adversary compared to success rates when following the outcome of a prediction and evaluating all traffic streams in the order of appearance in the prediction. This also takes into account those cases in which the adversary cannot access the exit traffic. We also present another experiment from a different scenario in which the adversary actively interferes with circuit establishment by triggering client-side DOS mitigation at the guard relay, forcing a client to use a new guard and to create new circuits with new exits. There's also a discussion why these issues are not easy to fix, because, for example, adding delays to circuit establishment would have a negative impact on the performance in Tor. In summary, we presented approaches to estimate or improve the success chances for traffic analysis attacks by reasoning about whether or not Tor exit traffic on a target can likely be accessed by an adversary and how one could strategically act to estimate those chances. This is the end of my talk, and I am now happy to answer your questions. Thank you for watching this video.